I'm Bob Bitmead. I'm from the Mechanical and Aerospace Engineering Department. I have credentials in electrical engineering, and I'm introducing the distinguished speaker for the Computer Science and Engineering Department. And I think that's a good symptom of the subject of robotics in the Jacobs School, is that it tends to blur those boundaries between areas. And I'm very pleased to introduce Henrik Christensen. He's the Kuka Chair of Robotics and Executive Director of the Institute for Robotics and Intelligent Machines at Georgia Tech. He's held that position since 2006 and was really central to the activities there in the emergence, coordination and leadership of the robotics research. Prior to moving to Georgia Tech, Henrik was the Chaired Professor of Computer Science at the Royal Institute of Technology in Stockholm, Sweden. His PhD is from Aalborg University in Denmark from 1989, and he was on the faculty there before moving to Sweden. He's very well versed in the academic, industrial aspects of robotics in the modern world. He's an IEEE Fellow and a Fellow of the American Association for the Advancement of Science. He's also deeply involved in the policy side of robotics, and he's Editor-in-Chief of Trends and Foundations in Robotics and was editor of the US National Robotics Roadmap in 2009-2013. He's speaking to us today on the subject of model-based vision for robot applications. So please join me in welcoming Henrik.
Thanks, and thank you for allowing me to talk about this. I'll try and break the talk into sort of two sections. The first one, I'll talk about some of the science I do, and then I'll talk a little bit more about my vision for what a robotics institute could be at UCSD. I wanted to start out by talking about some of the science. I'm fundamentally interested in how to apply estimation methods to figuring out how we solve real-world problems. I'm a very practical guy. If it doesn't work in the real world, why bother? So that's for me. So I wanted to talk about this as an example of, I typically would say I apply my research in three different areas. One of them is building maps, 3D maps of the world so right now I have somebody that's using 3 aerial robots and 5 ground robots to map out the Aberdeen Proving Ground in Maryland. But that's sort of one area of applications. The other one is, how do we build user interfaces for these intelligent kinds of systems for everyday people? And that's remarkably hard because you can't really make anything. So my prototypical user is my 80-year-old mother who's never used a computer. And if you can design a user interface for her, you can do it for anybody. And the third area I work in is visual tracking, and it sort of dates all the way back to actually where I started to do my work. So I'm very interested in, how do we build robust systems that can make this happen? So how do we go from these kinds of applications that are sort of highly structured to doing this? How can we operate robots in everyday environments? And for those of you that have kids, you know that this is a partially structured world at best. So how do we build robots for this and not having sort of deep learning and all of this? So how do we do this? So things like pick and place tasks and moving to sort of relatively unstructured environments. And how can we do this robust? So how can we do this all the time? And actually, even here, for these kinds of pick and place tasks, just to give you a data point, the average grocery store has 45,000 different items on the shelf. Today, we have techniques that can handle 2/3 of those. That just leaves another 15,000 we don't know how to process. So there's an interesting challenge there in how can we do anything from hairnets to toothbrushes to all sorts of things, which is really hard. So that's one of the problems I'm very interested in. And the other thing I'm very interested in, how can we actually use prior knowledge? Trying to do this by opening your eyes and looking at the world alone is too hard. So I'm very interested in, how can I use some kind of 3D models to basically build a process for this. And there's been, the bad news is people have been working on this in 1965. So Roberts, 1965, thought this would be a summer project at MIT. Well, as long as they have long summers up there. But getting down to it, so there's lots of people that have done this over the years, and we made tremendous progress. But it's still a really challenging problem. So what we're after is, can I do this for objects with and without texture? So can I do it for objects like these that are almost transparent? Can I do it with background clutter? I'll come back and talk about this in a minute. Can I do it where I have discontinuities in space and time? And can I do it in real time? Well, some people, like one of my good friends, Gösta Granlund, is as long as you just choose the right problem, real time can be very tractable. Tracking the moon is within our reach, but tracking tennis balls might not quite be in there. But anyway, that's what I'm after. So I want to be able to do textured objects, anything from these to these things. Can I build a robot that would set the table for doing this very well? And typically we would have photometric information, so appearance information, and we would have geometric information. We would like to be able to use both. We would like to be able to do clutter, anything from relatively clean industrial environments over, it's not quite my office, but it could have been my office, to home environments like these that are highly unstructured. And I know some of you are going to say, homes don't look like that. That's sort of an overstatement. Well, let me ground you. So I did a study with iRobot where we went to 100 homes and deployed Roombas. And it was sort of like a dating study. I equivalent it to dating a beautiful woman. So you see it first, you see the woman on the web and said, this is going to be interesting. Then you meet and then you figure out, are you going to go steady? Are you going to go on? And are you eventually going to get married? We did the same thing with robots. We called up people and said, can I give you an autonomous vacuum cleaner? Some people said, no. And some people said, oh, this is going to be really cool. You went out and you gave them a vacuum cleaner, came back a week later and said, are you still using your vacuum cleaner? Came back a month later and said, are you still using your... And then we came back 6 months later and said, are you ready to get rid of it? One of the first days we arrived in a home, it looked like this. This is the boys' room and this is the girls' room. And we said, okay, this could be a small challenge, If you put yourself down on the floor, this is rugged terrain. Came back 2 weeks later. He had cleaned up his room because otherwise he couldn't use the robot. So some boys are early adopters. The girl was, maybe not. But you know what? Came back 6 months later and they both cleaned their rooms because otherwise they couldn't use the vacuum cleaner. What's the real take-home message here? For $199, you might be able to get your kids to clean their room. But anyway, these rooms, there are actually real clutter out there. So it's important that we can operate even in those kinds of environments. We want to be able to handle all sorts of challenges in terms of, how can you actually do these kinds of discontinuities in space and time? In many cases, you need to be able to have techniques that not only can do effective tracking, but also can do very effective initialization. And we want to be able to do real time so that you can do it so that it will actually work. And here we're primarily using GPUs to be able to do sort of parallel mechanisms that would allow us to do this very effectively. The good news is that GPUs are sort of taking off, so access to computing power per dollar is actually going down dramatically. So when I started doing robots 20 years ago, computing power was really expensive. It was very hard to do. I was actually on the team that developed the first autonomous vacuum cleaner before the Roomba. It's called a Trilobite for Electrolux. The bill of materials for all electronics and all computing was $50. We were allowed to spend $1 on the computer, and we couldn't make the assumption it had a floating point unit. That makes it sort of an interesting challenge. The good news is I can now say that I've developed a robot that truly sucks, and in this case it was a good thing, So, and we sold 400,000 units, and then iRobot came out with their robot, and since then it's been 10 million iRobots. But that's important. So we're very interested in how can we do this. So one of them was, can we build 3D models, and can we make the assumption that you have sort of prior knowledge? The good news is that Trimble, former Google 3D Maps, and others are building these amazing number of 3D models. So there are more than 3 million different models out there. Anything you can buy in an IKEA store has a 3D model in Trimble's 3D warehouse. Initially, I was very skeptical. I'm saying, these are built by hobbyists, what do they know? They're amazingly good. So there are people that have a lot of time on their hands that want to do home decoration, and they actually provide these 3D models, and we can use them straight off The bad, in most sort of manufacturing process, you can make the assumption they have a CAD model. Because, who would build something if they didn't have a CAD model for it? You can always make the assumption it's an electronic CAD model. So just to give you a data point, the Lockheed Martin builds the C-130J, the big bomber airplane. They've done this since the 60s. They only have paper CAD models. Or they only have paper models, drawn models. They haven't digitized it yet. So a lot of the airplane, the same thing for Boeing. They still have airplanes where they don't have a 3D model for. But for the rest of the world, we can make the assumption that we have 3D models. And the good news is that we're getting depth sensors from everywhere. So it started out very much with Israeli companies that were acquired by Microsoft that were building these 3D models. Then Microsoft decided they don't want you to use this sensor, so they wrote into their licensing agreement, you can play as much as you like as long as you don't build a product. So then Occupital came around. They were doing this Project Tango. PrimeSense came along and Apple acquired it. And now we actually have Intel is coming out with the RealSense. So we are getting these 3D sensors. They're dirt cheap, and they're actually very effective. So the advance on FPGAs and other things and optics has allowed us to come up with really good sensors. So we're interested in this in terms of figuring out how can we do 3D tracking, how can we do this in a way that is very effective. I'll talk about two different approaches here. One using purely 2D information. There are still cell phone applications where you can make the assumption you have a 3D camera. And then I want to talk a little bit about 3D. So want to combine photometric and geometric information into this. So think about this as being a tracking system where I have an image, I have a bunch of prior models. I can now over here run a loop that do initialization and one over here that do tracking. So I'll start out by figuring out what is the best matching, image matching for this to get sort of a coarse estimate of what is the overall pose. Based on this, I can do sort of very simple alignment, figure out, you probably can't see this from the back rows, but there's some red areas here that's basically the parallax on the difference between the model and my estimate. I use this for doing updating, and now I can do real-time tracking. That was not hard. The good news is that if you go in and you actually do this, so we have a set of edges here, we have a model rendering. If we do it here, you can actually see this will track very reliably. If you did this sort of based on key points only, it would be not very reliable. And the real trick here is that I can actually do this because I'm matching an entire model to a set of edges. If you only matched individual points, it would be very, very noisy, sort of what you're seeing over here. So that works really well. But really, if you want to do this so that you can initialize it, you need to figure out how you can maintain multiple hypotheses. The way we do this is we basically have what is called a particle filter, where you have a federation of particles that you're using to maintain different kinds of hypotheses. That allows us to do more effective initialization. It allows us to have interesting motion models for these. It allows us to be able to do auto reinitialization. So basically, we want to be able to figure out where our set of features on this to do effective tracking. We want to be able to find this. We want to have a relatively simple, it's still only a first order motion model. And then we want to be able to use this so we can do reinitialization. So here you're seeing the tracking. We're basically counting the number of hypotheses that's supporting a particular pose. Then we go out and then we come back and immediately it will sort of reinitialize and actually get very reliably, because whenever you lose the number of particles here, you basically do a uniform distribution over your parameter space, and that will then very fast recruit this. So we can do effective tracking, coming up with a very nice way of doing tracking over time, even in the presence of very significant motion. You can see that it will actually do this very well. And then, here we go. So we did a bunch of experiments. So, this was too simple. Anybody can do this. Almost anybody. So the red one is if you only had one particle, eventually it's going to fall off in your host. So instead, we can come in here with the particle filter. It will be very reliable. We've done this on CAD models. This is a CAD model from GM. It's not a pink Cadillac. It's a black Cadillac. But it will still do very well. And you can see how we can do reinitialization, even with very few particles. And this is now effective enough. We can do this on a cell phone. We can do this on an iPhone and actually get very good initialization. So here's an example where we're doing this. This is a project where We're picking up this water shield, we're putting it on a car door, and we're sealing it. So we're doing this because people are really bad at doing this. So if I told you, take a roller, apply it along the edge of this seal with 10 newtons, none of you would be able to do it. It's just, we're just not very good at sensing what is 10 newtons. And that implies that, for instance, we worked with the BMW factories on doing this. So how do you solve this problem if you don't have a robot? It's very simple. Have a guy, he does this. We know that he fails. Okay, we just put a guy next to him. And he also does, and then it's still not quite good enough. So we just put another guy next to him. And that implies that the way BMW have done this traditionally is that they've had 3 guys that did this repeatedly. And we all know, if we go and buy a BMW 700 series, you take it to the car wash, there's water in the cabin afterwards, you can say, really? I paid this much money for this piece of crap? So BMW couldn't accept this. So for that reason, we built an application for them that would allow them to go in and basically pick up the seal, do this very reliably, and that's now being deployed actually at a BMW factory in South Carolina. So that's an example. Stop doing that. Here's an example at the Peugeot factory in Paris. And we have a person that comes and stands in front of it, and it's still reliable enough that we can track it in the presence of this person that's doing it. And we did this recently for the Boeing factories. This is a piece of a wing panel, and you have a CAD model, and it allows us to go in, and we can now do positioning at 0.1 millimeters. So it would allow me to go in and replace this robot for being able to do drilling for these kinds of operations. It's not a real wing because Boeing is not crazy about giving us CAD models for real airplanes. But this is where traditionally you used machine tools to be able to get very, very high precision by closing the outer control loop, by using vision with a control system, with the motion control of a robot. We can now replace machine tools. And this allows me to give a much higher degree of agility to a process so that you can manufacture several different airplane models at the same thing. So this is getting deployed right now in a Boeing setup for being able to actually build real airplanes. And one of the reasons for this is that Boeing has a problem that most of us would like to have. Their backlog is 7 years. So when UCSD decides to buy a new Boeing 737, the chancellor can pay today, but he'll take delivery 7 years from now. Knowing Pradeep, he's not going to be very happy about a 7-year wait line. So that's going to be a challenge. We are trying to work with them on doubling their manufacturing capacity. How can we get from 60 airplanes a month to 90 airplanes or to 120 airplanes a month, which is an interesting challenge. Great, so he can do this. But how would you be able to do this on textureless objects like my water bottle here? So, well, the good news is that I can still go in. This is a water glass you can buy at the IKEA store. The good news is I can go to my Trimble 3D warehouse and I can also get a model of it, so I can do this. And now I can basically just use my standard graphics CAD model, and I can generate a number of different projections. I can use this to initialize my model and come up with a very simple way of doing sort of initialization. So I can now go in and do relatively simple chamfer matching, and by doing this, I can come in very reliably. So this is the best we can do. And I love wine, so for me it's a good thing that I can have my robot track my wine glass. Maybe it's a bad thing if it knows how many glasses I had, but that's a different discussion. But here you can see that in the presence of all sorts of background clutter, we can track this object even though there are many, many more edges in the background than there are in the foreground. So you can track largely transparent just because we are optimizing on an overall model that allows me to guarantee robustness in the presence of this. So that makes it very attractive that we can go in and build these kinds of models. So I don't have time to go in and give you much of the details, but there's some nice publications out there. I want to do this in 3D as well. So this is a big problem. How can I do bin picking? You have a heap of parts, and I want to know how can I pick them up. So we have a 3D sensor up here that will go in, recognize the models of these, and being able to put them in particular places. There are lots and lots of applications in industry where, don't ask me why, but what they do is that they have these coming out of a machine, structured, coming down a conveyor belt, and then they throw them into a heap. So they changed it from a very structured problem to an unstructured problem, but such is life. So we just want to be able to pick these up and put them in the right order. And so what we're really after here is, if I have a 3D model like this, how can I, in the presence of noise, occlusions, and clutter, pick up these pieces, do reliable pose estimation, and find them. And here are sort of the kind of poses that we come up with by basically doing matching. So the question is, how should we do this? Basically, the idea is that we would have a CAD model, have a 3D sensor, basically using the equivalent of a GPU to render a large number of views of these, and then use those to figure out sort of faking sort of feature extraction based on a rendered model. Use this to build a hash table so that by the time I have real data coming in, rather than trying to match it with a very complex 3D model, I can just do a hash table lookup. And by doing this, I've now turned it from a problem that's computationally very challenging to an almost trivial computational problem. So, and the good news is that I can do all of this offline. So basically what we do is that we go in, take a bunch of different features, surface point, boundary points, surface and boundary points. There's a bunch of simple metrics that you can use for sort of doing feature comparison, which is not that hard. Once we combine those, we can basically take a CAD model. We can then generate a bunch of different feature representations here that allows us to do, you tell me how much computing time you have. Based on that amount of computing time, here we can go in and basically render as good a hash table as you want. And in general, memory is cheap today. So it's not that hard to get to reasonably good models. So what we're doing here is that we're trying to take away all of this, move it into this, and then come up with a pretty good model. If we'd only done individual features, we would have a non-robust systems. We would have had a number of false positives on each of them, but once we combine it into sort of a joint feature representation, the number of false positives is reduced very, very significantly. So we can do this, come up, we can manage these kinds of things, which is actually very typical. So I work a lot with Boeing. They don't have a lot of these, they have a lot of these. And can we do this? But I still want to be able to also do this. And I don't know how it is at UCSD, but at Georgia Tech, this is what you find on a graduate student's desk. I am encouraged they also have detergents here. So apparently they wash their clothes every now and again, which is not one of the things I thought I would find in there, but they have tea. The light apparently goes out every now and again. Georgia Tech boss, tools, so they're real roboticists. They drink coffee, they have tea, all the things you would expect. So the question is, can we do this? So to do this, we added color. So we wanted to be able to not only do this, but we wanted to be able to also do 3D models for this. Basically, we just added another dimension to this so that we would have not only the geometric information, but also color information as another set of features. And then we can do this, go in, use exactly the same model way of doing this, doing it on a GPU so that we can do it in real time. And it turns out that it's relatively simple to do most of this directly on this. So here are the kind of models we're using. Actually, in this case, we used models that we rendered directly from our 3D camera. Did evaluation, how much noise can we handle? Most of these depth sensors are not very good. So typically you will find somewhere around 5 millimeter noise in the depth cloud. So this is actually closer to reality than this is. We want to be able to have multiple objects in the same instance, or the same instance but multiple cases. We want real cluttered scenes, and then we wanted to be able to sort of see how well does it compare to what state of the art is. So here are our cluttered scenes, pretty good. We went in and used some of the standard techniques. This is one of the reported techniques in the literature. Would not be my first choice. It didn't recognize anything. But sometimes if you choose your data set correctly, you can publish papers. Here is one where we did iterate the closest point, gets up some. Here is a couple of other techniques. And then finally, we actually get many more. We didn't get all of them. But in some sense, that doesn't really matter. Because in many cases, what you do when you do bin picking is that you pick the chop set. And as you go back and sense, you can slowly get to it. So getting to 100% perfection is overdoing it. But we want to get close enough that we can go in and do this for real world objects. So here you're seeing we're coming in a bunch of data sets for being able to pick everyday objects, and actually in most cases we're getting pretty close. It's good enough that we can do this and get real sort of data instances of doing this, and we can go in and pick it. So we're using this today to pick objects for grocery stores. Almost anything in the toiletry aisles is a single pick, primarily because if you go to most grocery stores, they have no storage capacity. Whatever they have is on the shelves, and that implies that you can deliver sort of a box of 48 tubes of Colgate toothpaste, because where are you going to put it? The chance that you sell 48 tubes of toothpaste tomorrow is 0. So for that reason, we need to figure out how we can pick these individually. So this is being tested right now at a facility in Boston. There's a Amazon competitor, a company called CNS Wholesale. They deliver 30% of the groceries to the East Coast. I don't think they're on the western side of Mississippi. But there it's very important to actually be able to go in and do this fully automatically. We didn't test it. Some of you might know there's something called the Amazon Pick Challenge, where Amazon set up this challenge. They've been run at the last couple of conferences to do the Pick Challenge. And it sounds very enticing. If you're a student at a robotics center, for $25,000, you can win and you can walk away, and it's really good. You should read the fine print. The fine print tells that you're giving away all your IP to Amazon. I'm not giving away any of my IP for $25,000. So I have to pay for the work, and then I have to give you the IP afterwards. That sounds like a bad idea. But people have done this. So we haven't, for that reason, I can tell you we've done comparison, but this is still sort of where we are in terms of doing this. So the other thing is that I'm very interested in how can I do this for some real world scenarios where I can do this. So I'm interested in having a rich set of objects. So I mentioned before, in the Trimble or the Google 3D warehouse, there are a number of these IKEA models that are being used, and they're actually pretty good at doing this. So I said, okay, let's test this. I don't know how it is in San Diego, but in Atlanta, most of our graduate students have IKEA furniture. So I said, this is not hard. I can go to one of their dorms and use my standard models, and we'll see how well it actually works. And it turns out that you can go in, you can find this, and this is the particle cloud here. So the centroid is where they estimate that the position is of this particular table. You can see this shelf, you can see the bed, and you can see the couch. So it's actually remarkably good. So we can use it to drive around in a home environment using this sensor that's $99 and a particle cloud, and actually come up with a very reliable estimate. We can do this in real time using a bad GPU, so a $199 GPU, and get really nice results. So for this part, I want to say, so we're really getting to where we can use these sensor systems in everyday scenarios to get to very unstructured environments and have very good models. We can do object perception regardless of the amount of texture you have in your environment. So we can do this. I mentioned we've done this for dorms, we've done this for wine glasses, we've done this for everyday environments by basically combining photometric and geometric knowledge. So why leave yourself? Computing power in general is cheap enough that you don't have to limit yourself. We can do this in a highly cluttered background. Basically, we're doing this by using a particle filter that allows us to manage the weak. So in most cases, you can make the assumption that it's a unimodal probability distribution that's using this. But the good news is computing power will help us with this. And we can handle sort of post-tracking and estimation as a combined process. And basically, computing power is cheap enough that it's very easy to do this. So that was sort of the first part. I want to talk a little bit about contextual robotics at UCSD. And where do I see this going? So I'll sort of divide it into 3 parts. The first one is, how do you build successful research environments? So as was mentioned in the introduction, I'm at Georgia Tech today. We started out 9 years ago. And today we have 70 faculty and 300 graduate students. And I would say we're only beaten by CMU today in terms of size. So the question is, how can we do this? How can we build these? And then to me, it's very much about how do you build sort of a federated system for, so how do you build sort of multidisciplinary research? I'm very interested in building sort of what I call cognitive systems. It's not the coxi here, it's really, how do I build systems that are smart? Not only sort of for doing this. So my objective is, my vision is I would like to build a robot that I could take home, give it a tour of my new house in Carmel Valley, and then basically say, this is where the living room is, this is where the kitchen is, this is where it is, and then be able to drive off to the grocery store to buy some groceries for my new house, and by the time I come home, the robot said, I found this other room, can you tell me what it is? It should be smart enough to explore on its own, it should be smart enough to understand what contextual analysis, it should be smart enough to when I say, could you bring me a bottle of Coke? Then, I'm from Atlanta, that's why it's Coke. But there, it would be able to know, we typically find Coke in the kitchen, get to the kitchen, there's probably a refrigerator, how would I be able to do this? And how would I be able to leverage the cloud in such a way that if I teach one robot and I get a new robot, I don't have to start all over again. It's sort of like, why not use the cloud to be able to know what is the common sense knowledge, share skills over time? So I really am interested in all of this. And that requires us to think about mechanical aspects, control aspects, computing aspects, human-robot interaction aspects. I mentioned this to some of you before. I was on the team that developed the first vacuum cleaner, and I'm very, very proud of this vacuum cleaner. So I went and I gave it to my mom, and my mom came back a few days later and said, Henrik, there's a problem with your vacuum cleaner. It drives around in circles. I said, oh, Mom, it's not a problem. Go into the menu, press the third button, and we're back. And her first question was, what's a menu doing in my vacuum cleaner? She's never used a computer. So for her, a menu is something you get in a restaurant, not something. So how do we make this accessible to everybody, not just the nerds? The other is that we also need to make it accessible. I don't know if you know that data point. The average 20-year-old American male has spent 12,000 hours playing computer games. That's 3 years with no sleep. So if I can design a user interface that looks like a computer game, they're instant experts. I don't do computer games at all, so I'm going to be looking at the red button is for what? But who cares? How do we make this spectrum of technologies available so that everybody is an expert? To me, that's very important. I see collaborative manufacturing being one of the areas we're seeing tremendous opportunities of working with people, not sort of lights out factories. I don't really believe in lights out factories, but I believe very much in how do we build sort of the optimal between sort of these robots. How does it understand what I do? So we have a robot we're trying to build in Atlanta that helps me I love to cook. So if I have to make pasta bolognese, I would like to be able to just give the recipe to the robot, and it works in concert with me. So if I pick up the meat, it'll go off and pick up the carrots, or it'll go and pick up different things. So it all the time works in concert with me. That requires you to be able to have context awareness, understand activity recognition, and build real systems. And I don't want to have to spend hours programming the robot. I'm trying to make food here. So I want to give it the recipe and it'll figure out the rest. So that's an interesting and in some sense that is manufacturing. But also clearly there are lots of service applications, both in real world services, but also in the home. I don't see most of the home applications being business viable in the short term, but I see them in the long term. So how do we get to where we can work on this more generic stuff? And then I'm a deep believer in that unmanned systems, both ground and aerial. There's a lot of focus on unmanned or driverless cars. I think it's a little bit overhyped right now. My own prediction is that we will be 15 years out before we really get lots of driverless cars. So my own prediction is that kids born today will never drive a car. And I think a lot of the obstacles will not be technical, it will be legal obstacles. So we should figure out how we can do all of our test driving in Europe where they don't have punitive damages. So for that reason, it's much easier to train it in Europe. Once we understand what the error distributions are, we'll deploy them in the US. I have friends in Denmark, so we can start by driving in Denmark. The other is that for aerial vehicles, I actually think by 2020, we will see pilotless air freight coast to coast and transoceanic. The only limitation today is really legal. We can do this. And if I look at it, I flew out here, it took 5 hours yesterday because of storms and stuff like that. The pilot spent 15 minutes getting in the air, and then he had 4.5 hours to play Angry Birds, and then he landed again. I want to take out the Angry Birds part of it and just have him manage a fleet of vehicles so that he can be much more effective. He doesn't have to leave his family. There's all sorts of good things that's coming out of this. This is going to come relatively quickly. We're talking to Congress right now about how to do this. So you should expect to see this. Still lots of user aspects of this, communication aspects, how do we do this? And of course, there's legal aspects we have to take into account. But to me, it's about how do we empower faculty? Faculty cares about how do I become famous, how do I get more money, and how am I more visible? Okay, that's what we are about. How can I help them be more visible? How can we write bigger grants rather than smaller grants? So if you look at it, fundamentally, you spend the same amount of overhead on a one PI project as you spend on a multi-PI project. So let's stop all of this and just go for ERCs so we can get sort of real money. And I think it's actually very realistic. Same time, I think it's important to have shared resources. It's very hard if you only invest in infrastructure on a single PI basis to really become big. So we want to have big, sort of large-scale resources for doing this. I think it's very realistic to be at least number 3, maybe number 2 in 5 years in the US in terms of robotics. And I think in terms of collaborative robotics, it's possible for us to be number 1 in the world in 5 years. So I think that should be sort of the objective. And then I think there are various kinds of building communities. Some of them are just simple things like having weekly seminars where everybody sort of gets to know each other. I still remember when I started in Stockholm, and Anders Lindqvist, who's a very famous applied mathematician, came to me and said, "What do mechanical engineers that motivates research? Do they put bolts together in new ways, or what do they do?" And then the mechanical engineers came to me and said, "Why is Anders in here? This math never works in the real world." 5 years later, they all came back to me and said, "You know what? I've learned something new. They actually do useful stuff." So very much is building having this, and my objective would be, if you're a graduate student here and you've been here for 4 years, you should have met all the big names in robotics. Anywhere from the Rodney Brooks to the rest of them, so that you go out and said, "You know what? I know all of the big guys in the world." That's very important for doing this. And of course, we want to suck their brain on to figure out what are the next big ideas. I would like to figure out how can we build an annual research summit. We should be the place where people get together to think about the hard problems. You already have a contextual robotics summit, but it's not about big thinking. How do we make sure that the 20 smartest people in robotics get together, not anywhere in the world, but at UCSD to think about the hard problems? And the hard problems 5 years out. And that's good. That's thesis topics for the next generation students. But we should be the place where the thought leadership comes from in terms of what are the interesting research problems. And then I think that there's a way of building, a community for doing industry and community research, making outreach sort of effective. At Georgia Tech today, we house the Southeastern US First kickoff. So we have 1,400 kids showing up on campus to talk about robotics. I win. So how do you make sure that all of the kids that want to do robotics show up here 2 years before they have to get admission? Their highest objective should be, how do I get into UCSD? We win. And of course, I mentioned, some of you know this, I wrote the US robotics roadmap. Through this, actually we are June 9th, we're going to the White House to talk about 5 years down the road what happened. Right now I'm writing a new version of this. And I know I'm in California, so I'm of course writing a Hillary version. But unfortunately, because of the rest of the country, I'm also writing a Trump version of my roadmap. I'm just hedging my bets to make sure no matter who wins, I win. So we're working with both of the transition teams to figure out what does the next generation thought leadership look like this. But it also implies that most people, when they have a robotics problem, start by coming and saying, "Henrik, we have a problem, can you help us?" In most cases, I can't help them and I point them to somebody else. But the fact that you get first right of refusal, you want UCSD to be the place where people go first. And then they might have to go somewhere else afterwards, but you want to be the gate. So I think there's a huge opportunity to have thought leadership in this kind of environment. I still haven't figured out how to do educational programs here. So I'll have to work with the chairs and the dean to figure out how do you build the educational program. At Georgia Tech, we started a PhD program, and right now we're starting a master's program in robotics. We have 20 students applying for every one slot. So to get into our PhD program, you typically have to have 2 publications and amazing grades and an amazing GRE scores, otherwise you're just not going to make it. So for us, this has been very attractive. Before we started our robotics program, as an example, in our ECE department, the best students did signal processing. Today in ECE, the best students do robotics. So that helps, that you can then try, once they've been admitted, to convert them and say, no, you should do something else. We're of course going to try and convince you not to do that. But anyway, having very strong, because they go out, they're very strong. One of my misgriefs is that whenever we graduate students at Georgia Tech, they leave immediately for Boston or California. So we don't keep them. We don't have a local industry. You have the advantage, you have a local industry. You can actually build a strong community here. Unless you're in cybersecurity, they're not going to stay in Atlanta, unfortunately. So for me, that's one of the things that makes San Diego very attractive. And we should build next generation leaders. They should, of course, be able to solve problems. They should be team leaders. And I think in robotics, it's very important. You have to have a holistic perspective where you look at mechanical, electrical, design, computing, interfaces. Because if you don't think about all of these, you're not going to be successful. So we need to really think about this over and over again. And then I think it's important to have a clear view of why does society care? We're here to build people that actually will have this. So they have to think about lifelong learning, and they have to think about what are the big societal challenges. One of them is aging, one of them is transportation, a big one is supply chain and material handling, new business models. So I think this, and then I think it's very important to build a track record of delivering. It's not enough to have the vision. You need to be able to show that you can deliver. And what's the right mechanism of working with companies to do this? And then if I look at the place we have at Georgia Tech, we have about 30 million a year in research funding. 1/3 of it is from industry. And I think if we worked hard at it, we could get it to 50%. The good news is that I only write a 2-page proposal, and I don't have to compete for an 8% acceptance rate from NSF. So I get around 4 million from Boeing every year, and I write a 1-page proposal every year. They come back and we do a dog and pony show for them, and they give me another 4 million. The fact that I don't have to write this, and then you can say, well, Boeing is very applied. No, it's not. Boeing does not allow me to work on any problem I can solve the next 5 years. They're sort of saying 1 year out, we're already doing it. 3 years out, we have companies that are working on it. 5 years out, we have no idea. You should work in the no idea space and impress us on what next generation technology is. So you're going to find lots of opportunities to work with companies to do really hard problems that are sort of interesting and out there. So I don't know what your finance rate is today for industry, but I think there's an interesting opportunity to grow the pie. And then you have all sorts of interesting local opportunities here that can be leveraged. So to me, it's very much about building a community of collaboration. You can only be successful in robotics if you do this. So we should do multi-PI projects. We should do, and the same, I want the junior faculty to be the PIs. I've already raised $200 million. Whether I raise 205 or 210, who cares? What I care is how can I empower the junior faculty to be the front leaders on this, and I can be the co-PI. So I will help to the extent, but at the end of the day, if we empower the federation of faculty, I win. So that's very important. I think it's important to build a strong brand and then address the truly hard problems. There's enough other people that are addressing the easy problems. Let them solve the easy ones. I think it's very important to have joint infrastructure. So I'm still talking to Al and others are figuring about how do we get joint infrastructure to make this happen. We can't build it on a federation of individual laboratories. We need to build on strong infrastructure. You have some good infrastructure here, and I think we can build in more. And my objective is to at least grow at 100% every 5 years. I think we can do it faster, but I'm not willing to sign a piece of paper with Al that says 3 years, but I think maybe we can do it in 3 years. So I think there are opportunities here to grow it. I think it's your chance to blow it rather than somebody else's. You have all of the right ingredients here in terms of great faculty, great students, a great community. this can be grown into something that can be a really big deal in a relatively short cycle. So I think that's very exciting. And with that, I think I'm at the end. I'll say thanks.